Hello everyone, my name is Khánh Lương and I am presenting the paper A Novel Approach to Learning the Consensed and Complementary Information for MultiView Data Clustering. This is the outline of the presentation. We will have introduction, related words, the proposed 2CMB method, conclusion and future work. So what is the MultiView data? MultiView data is the data where data samples are collected from multiple sources or represented by multiple types of feature, as shown in the example in the figure. The multi-view data clustering is a process to simultaneously clustering all view data to learn the accurate clustering solution. The multi-view data is deemed to contain the consensus and complementary information. The consensus information is how different data views embed a compatible latent structure within the data. The complementary information is how each view providing a diverse characteristic within the data. For example, in the multi-source news dataset, all data sources share some common information, which is the consensus information. But each data source presents some distinct information, which is the complementary information. So the challenge of multi-view clustering is to ensure learning both consensus and complementary information to help achieving the accurate clustering solution. Because the main aim of the paper is to develop a method that can effectively learn the consensus and complementary information, so we'll first investigate how existing methods deal to learn the two types of information. We know that learning the view shared and or view specific information is a long-standing goal in multi-view data. Many was focus on learning consistency or diversity only. Most methods learn the consensus information. For example, multi-view non-negative matrix factorization learns the consensus information by embedding the most common latent features from all views. MultiView spectral clustering by common agent vectors learns the consensus information by learning the common largest agent vectors from multiple views. MultiView coupled matrix factorization learns the consensus information by learning the common representation shared in multiple views using coupled matrix factorization. Only a handful of methods learn the complementary information. For example, diverse non-negative matrix factorization learns the complementary information by using a simple diversity constraint on low-rank representation of different views. Some subspace-based methods use the complex constraint HIC to identify distinct features in the subspace. However, these methods fail to ensure that enough consensus information has been learned. Few methods learn both the consensus and complementary information. For example, distinction-based consensus spectral clustering assumes there are two components in the new representation, the consensus and the complementary components. However, it uses HIC to enhance the diverse information learned from different views, and because it is a spectral-based objective function, it is effective on large scale and high-dimensional datasets. Consistent and specific multi-view subspace clustering also assumes there are two components in the new representation. However, it uses simple nuclear norm for the consensus component and the L2 norm for the complementary component. Partially shared latent factor is an NMF-based multi-view designed to learn both information. However, it uses label information. So in summary, a matrix factorization framework can effectively learn the low-rank representation for high-dimensional and sparse multi-view data. However, there is no unsupervised matrix factorization-based framework that can learn enough two types of information from multi-view data. Manifold learning technique is known as a technique to learn and preserve the local geometric structure when mapping data from high to low dimensional space. It is combined with matrix factorization framework to learn the low-rank representation that maintains the original local geometric structure. In MultiView data, the manifold learning is applied in two main ways. For the first way, it learns the manifold on each view data and allows the low-rank representation on each view data to respect its own manifold. This will help with learning the good view-specific information. However, it ignores the correlation among different views manifold. In the second way, learning the consensus manifold, which is the manifold that contains all manifolds of all views, and allow the consensus low-rank representation to respect the consensus manifold. This will help incorporate the associative relation among views and can help learning a more insightful low-rank representation. However, learning the correct consensus manifold is a non-trivial task. So an effective technique to learn the useful manifold from multi-view data is needed. In this paper, we propose to learn the optimal manifold, which is incorporated in a factorization-based loss function to simultaneously learn the consensed and complementary information. Before we go into detail of the proposed method, let's have a look at the multi-view data definition. We are given a multi-view data with NV views. SV is the data on view V. We would like to learn for HV and WV, which are the low dimensional representation and the basic representation of data in view V. The goal of multi-view data learning is to learn the most common low dimensional representation denoted as H star. This is the objective function of the proposed 2CMV method. For the first contribution, we proposed a two-component model as formulated in the first term of the objective function and illustrated in the figure. We can see that both NMF and CMF are utilized to factorize the input multi-view data. The NMF model will learn the low-rank representation HV on each view V, and this new HV will create HCOM, which is the complementary component. Simultaneously, the CMF model will help learning the consensus low-rank representation, which is H star. At the end, the final low-rank representation of the model will be the combination of both components as given in the figure B. As a second contribution, we propose to learn the optimal manifold, which is the most consent manifold, as illustrated as the intersection part of all manifolds in the figure. The optimal manifold is calculated from the optimal affinity matrix A-opt, which is calculated by taking the minimum affinity values from all views. Learning, so the second term in the objective function here is to learning and preserving the optimal manifold, which is to ensure that all data points residing close in the all views in the original space will be preserved to remain close in the new map space. For the third contribution, we propose to embed a complementary enhancing term. This is based on the concept of orthogonal constraint, and it is applied on the two components H star and HCOM to promote the independence or complementary information for the two components. In summary, the final objective function of 2CMV includes three terms. The first term is the two-component model. The second term is to learn and preserve the novel optimal manifold. The third term is to enhance the complementary information while protecting data to lower dimensional space. We also make use to trade-off parameters for manifold learning and for complementary enhancing term, delta and lambda. In experiment, we use a wide range of tests and image datasets to evaluate the performance of the proposed method and other benchmarking methods. This table gives detail of all benchmarking methods and their characteristics. We see that regarding to the adopted framework, MVCMF is the only method that uses Coupled Matrix Factorization model. Other benchmarking methods using NMF, while 2CMV using both. Regarding to type of manifold learned, LPDMF using learning each view manifold. NMF learn the consensus manifold, while 2CMV learns the optimal manifold. Regarding to the complementary information, DNMF and LPDNMF enhancing the complementary by imposing the constraint on pairs of view. 2CMV enhancing the complementary on the two components. We also make use two versions of 2CMV, 2CMV-OM, which is the 2CMV with the optimal manifold only, and 2CMV-CE, which is 2CMV with the complementary enhancing term only. The two tables show the clustering results of 2CMV and other benchmarking methods. We see that 2CMV and its variations can easily outperform other benchmarking methods demonstrated by higher NMI and accuracy on all datasets. Furthermore, we see that 2CMV also outperforms its which is an evidence that both optimal manifold and complementary enhancing term are needed to have a higher performance clustering performance. Furthermore, we see that LPDNMF, which learn the manifold on each view only, MMNMF, which learn the consensus manifold, are easily outperformed by 2CMV-OM, which only learn the optimal manifold. This is show that this is an evidence of the effectiveness of the proposed optimal manifold. We also investigate a separate experiment to investigate the change of the alteration of parameters and on dataset D1 and D5. You can see that 2CMV easily outperform other benchmarking methods on a wide range of parameter selection. In conclusion, we have proposed a novel integrated factorization-based two-component model, 2CMV, which to learn both consensus and complementary information. And we also incorporate the optimal manifold and the complementary enhancing term in the proposed model to learn correct clustering solution. In future work, we will analyze the update rule to investigate the effect of different components, and also we integrate the clustering identification with the low-rank representation into the objective function to build a unified one-step process of MultiView clustering. Thank you so much for listening.